This lecture is a prelude to Module 12. It is a review of complex math. You should have taken up complex math in your previous math courses or in high school, so this should be just a review for you. Why are we doing this review? In previous lectures, you learned that the relationship between voltage and current in a capacitor or inductor involves either differentiation or integration. Thus, in order to solve for the response of circuits containing inductors and capacitors, you need to be able to solve differential equations. Now, differential equations are not easy to solve. Whenever your sources are sinusoidal, there's an easier way, and it's called the phasor method. This method will be introduced in the next module. This method, however, requires familiarity with complex math. So that's why we're doing this refresher. Let's begin by defining what a complex number is. It consists of a real part and an imaginary part. For example, A is a complex number whose real part is small letter a and whose imaginary part is small letter b. J here specifies the imaginary part. J is the square root of -1. That's why you call it an imaginary number, because supposedly the square root of -1 does not exist. You'll find it amusing, however, that in EEE, the square root of -1 is used to model certain electrical engineering phenomena. In other words, maybe it's not really as imaginary as mathematicians think it to be. In math, you are used to using the symbol I to represent the square root of -1. But in EE, we don't use I because we reserve I for current. This complex number is in rectangular coordinate form. It is in rectangular coordinate form whenever the real part and the imaginary part are separately specified. Here are more examples of complex numbers expressed in rectangular coordinate form. The complex plane is a Cartesian coordinate system where the x-axis specifies the real part and the y-axis specifies the imaginary part of a complex number. This is our complex plane. So here are examples of complex numbers plotted in the complex plane. The number, for example, a equal to 3 plus j4 in the complex plane is shown. So this is the real part, which is 3, and this is the imaginary part, which is j4. So here's another example, b, which is 2.5 minus j, 3.5. Here we see a purely real number plotted in the complex plane. So by definition, this is not really a complex number. And also a purely imaginary number plotted in the complex plane. Okay, just to round out our examples, here is a complex number whose real part is imaginary and whose real part is negative and whose imaginary part is positive. And here is a complex number whose imaginary part and real part are both negative. Another way of specifying a complex number is through its polar form. Here, the complex number is specified by a magnitude and an angle. For For example, if we consider the complex number a plus jb and plot that in the complex plane, we can draw a line segment from the origin to the point A, and the magnitude of that line segment would be the square root of a squared plus b squared. The other parameter that we need to use to describe the complex number would be the angle that this line segment makes with the real axis, theta, and that would be equal to the arctangent of b over a. Thus, the complex number a plus jb can now be specified as the magnitude of a at an angle of theta. So for example, if we have the number 3 plus j4, the magnitude would be the square root of 3 squared plus 4 squared, which is equal to 5, and the angle would be the arctangent of 4 over 3, which is equal to 53.13 degrees. So here you have 3 plus j4 expressed in polar form. The trigonometric form can easily be derived from the polar form. So if we consider the complex number a plus jb, which is the magnitude of a at an angle theta, from the figure, we see that the real part is equal to the magnitude of a cosine theta, and the imaginary part is equal to the magnitude of a sine theta. Thus, we can write the complex number in this form. So this is now called the trigonometric form. Again, as an example, if we have the complex number 10 at an angle 36.87 degrees, in trigonometric form, that would be 10 quantity cosine 36.87 degrees plus j sine 36.87 degrees. Which, if you carry out the multiplication into the quantity, would be 8 plus j6. So this is polar form. This is trigonometric form. And this is rectangular form. The exponential form of a complex number is very closely related to the polar form. It is based on Euler's identity, which is shown here. Thus, if you have a complex number a plus jb, which in polar form would be magnitude of a at an angle theta, and in trigonometric form equal to magnitude of a quantity cosine theta plus j sine theta, in exponential form, that would be magnitude of a e to the j theta, where magnitude of a is equal to the square root of a squared plus b squared, and theta is the arctangent of b over a. So our previous example, 3 plus j4, can be written as 5 e to the j 53.13 degrees. You're going to have to be adept at performing computations with complex numbers. Let's start with addition and subtraction. This is most easily done in rectangular coordinate form. So for example, if a is equal to a plus jb and b is equal to c plus jd, the sum, a plus b, would simply be a combination of their real parts plus a combination of their imaginary parts. So that would be a plus c plus j, b plus d. And the difference between a and b would be the difference of their real parts plus the difference of their imaginary parts. So that would be a minus c plus j, b minus d. So let's take an example. This should be very trivial. If a is 8 plus j6 and b is 4 plus j10, the sum, the real part would be 8 plus 4, which is 12, and the imaginary part would be 6 plus 10, which would be 16. So that's 12 plus j, 16. And the difference, the real part would be 8 minus 4, which is 4, and the imaginary part would be 6 minus 10, which is minus 4, so that would be minus j, 4. Let's now go to the multiplication of complex numbers. If a is equal to a plus jb and b is equal to c plus jd, in rectangular coordinate form, we actually have to distribute this addition into the multiplication. No? This is just the distributive property of multiplication. And we are going to generate the following terms. You're going to generate a times c, a times jd, jb times c, and jb times jd. So that's AC, JAD, JBC, and J squared BD. But J squared is negative 1. So putting together the real terms, that would be AC minus BD, and putting together the imaginary terms, that would be AD plus BC. It's much easier to do this if the operands were in polar form. The rule would be to multiply magnitudes and add angles. A times b, which is equal to magnitude of a at an angle theta of a times the magnitude of b at an angle theta of b, would now be the magnitude of a times the magnitude of b at an angle theta of a plus theta of b. This is very easy to prove if you consider the exponential form of the complex number. A at an angle theta of a in exponential form is a e to the j theta of a. And this b is b e to the j theta of b. So if I multiply a and b, that would give me magnitude of a, magnitude of b, e to the j, thetas of a plus thetas of b, which in polar form would be exactly the same as this. So again, let's take an example. Let's say a is 3 plus j4 and b is 4 plus j3. So if we do this in rectangular form, again, you have to distribute the addition into the multiplication. So you generate the following terms. That's 3 times 4 is 12. 3 times j3 is j9. j4 times 4 is j16. And j4 times j3 is j squared 12. But what is j squared 12? This is minus 12. So minus 12 plus 12 is 0. We end up being left with j9 plus j16 or j25, or 25 at an angle 90 degrees. If we had done this in polar form, all we would have had to do would be to multiply magnitude, so that would be 5 times 5 or 25, and add angle, so that would be 53.13 plus 36.87, which is 90. So notice the two results are exactly the same. Finally, let's take a look at division. So if I have a equal to a plus jb and b equal to c plus jd, if I try to get the quotient a over b in rectangular form, that will be a plus jb over c plus jd. Now what we want to do here is we want to place this in the form a certain value, let's say x plus a certain value j times y. We want to put this in this form, x plus jy. To do that, we would have to make the denominator, we would have to remove the imaginary part from the denominator. So how do you remove the imaginary part from the denominator? What you do is you multiply the numerator and the denominator by the conjugate of the denominator. So that is c minus jd over c minus jd. Our denominator now becomes c squared plus d squared. And these are now the terms generated at the numerator: ac minus jad, jbc, and minus j squared bd, which is equal to bd. I now separate in the numerator the real part from the imaginary part, and this is what I'm going to get. So this is now my real part of a over b, and this is my imaginary part of a over b. If we had done this in polar form, the rule would have been just to divide magnitudes and subtract angles. Again, this is very apparent from the exponential form of the complex number. So a over b would simply be the magnitude of a divided by the magnitude of b at an angle of thetas of a minus thetas of b. So let's try an example again. If we wanted to divide 3 plus j4 by 4 minus j3, to get rid of the imaginary part in the denominator, you would have to multiply both numerator and denominator by 4 plus j3. So the denominator becomes real, 4 squared plus 9 plus 3 squared, or 16 plus 9. And then if you take a look at the numerator, the 12 cancels out. So we're left with j25 over 25, or j, or 1 at an angle 90 degrees. In polar form, it's very easy. 5 divided by 5 is 1. And then you have an angle 53.13 minus negative 36.87, and you get 90 degrees. So again, exactly the same result. An operation that you should expect to encounter often is getting the conjugate of a complex number. The conjugate of a complex number is its mirror image with respect to the real axis. So for example, the complex number a, we get the mirror image of a with respect to the real axis, we get a conjugate. The asterisk signifies that that is the conjugate of a. So what is the conjugate of a complex number, or how do you get the conjugate of a complex number? One way is just to make the imaginary part negative. So if originally the imaginary part were jb, we now make it negative jb. The other way is to make the angle negative. So originally the angle was theta, now we might make it negative theta. So that's how to get the conjugate. Again, these are trivial examples. The conjugate of 3 plus j4 is 3 minus j4. The conjugate of minus 4 minus j3 is minus 4 plus j3. So if our complex number had a negative imaginary part, its conjugate would have a positive imaginary part. So if the complex number had been 5 at an angle 53.13, its conjugate would be 5 at an angle minus 53.13. For b, which is a negative angle, the conjugate would have a positive angle. Fortunately for you, you live in a time where a lot of complex calculations or computations you need to make can be done with your scientific calculator. For example, if you had a Casio FX570EX, this is a complex calculation mode which you can select by pressing the menu key and using the cursor keys to select the calculation mode. In this particular case, you would use the select keys to select this mode. Then you press equals, and that will bring you to complex calculation mode. In the Casio and other scientific calculators for that matter, I is used to represent the square root of -1, which is consistent with mathematical convention. It's only electrical engineers that use J to represent the square root of -1. So you can do complex manipulation with your calculator. So in this particular example, you can add 1 plus I raised to the 4th plus 1 minus I squared. You can perform computations like that. Okay. You can add a real number to an imaginary number. Okay. You can convert from polar to rectangular and from rectangular to polar. You can choose to have your results in either rectangular or in polar. You can do things like getting the conjugate of a complex number. You can get absolute values of complex numbers, of arguments of the complex numbers. You can extract the real part and the imaginary part of a complex number. So these are some of the things you can do with your Casio scientific calculator. Other scientific calculators would most likely have the same features. So it's just a matter of you familiarizing yourself with the features of your calculator. Now, just because these capabilities are already in our calculators, does this mean we no longer need to know how to manually perform complex operations? Unfortunately, not. Your calculators can do the work for you when your operands are completely specified. But when your operands have variable components, you have no choice but to carry out complex operations manually. So you still need to master the material in this lecture. Make sure you're familiar with complex math before you move on to the next module, which is steady-state AC circuit analysis using phasors. Otherwise, you won't be able to keep up with the material that's presented in that module. Thank you.